Hello, my name is Vladimir Simic, and on behalf of my colleagues Milos Kojic and Milosevic, who are also contributors to this work, I'll present you implementation of our SMIR methodology in finite element modeling of mechanical problems in composite media. First, I will introduce you to our SMIR modeling concept and its purpose in modeling of multi-scale biological medias. Then I will present you extension of SMIR modeling concept to mechanics of composite media and a formulation of new composite SMIR finite element for mechanics, or shortened CSF-EM, which is a new step in modeling complex media, including mechanical properties and behavior of models. The presented concept may serve as a basis for modeling tumor growth and in some other applications. Also, SMIR modeling concept and composite SMIR finite element for mechanics, they offer accurate predictions and can replace complex modeling of detailed biological systems. And accuracy of this CSF-EM is verified on the test models and applied in comparison between detailed 2D model, which consists of cells and extracellular space, and equivalent SMIR model. Motivation for this methodology development lies in something that we tried a long time ago, and during these years we figured out that three-dimensional models of complex media, organs, and capillary branching in general require significant effort in the 3D finite element generation and are computationally pretty demanding. And therefore, this SMIR modeling concept offers a simplification in obtaining complex tissue deformation, as in case of tissue with tumors or heart wall. Now, let's just briefly describe motivation for formulation of SMIR concept. One approach in modeling problems within complex composite media is to divide the entire domain into subdomains occupied by one constituent with the corresponding laws and properties and formulate the subdomain models. Then the next step is to model the interaction at the domain common boundaries and generate the model for the entire system and solve for the unknown describing the problem. This approach requires, in general, a significant effort to specify all internal boundaries between domains, and that is, if they are visible. And therefore, desirable is to have simpler models which take into account media complexity, but with given satisfactory accuracy. Now, to introduce the SMIR methodology and its purpose, we first consider a detailed model given on this figure A as a composite medium, that is medium composed of continuum domains, or so-called compartments, and a network of fiber-like 1D domain. The continuum domain includes extracellular space, cells and organelles, and capillaries and lymph vessels, and also neural fibers are represented by 1D elements within mesh of continuum domains, while 1D domains have their own 1D finite elements with the coordinate axis along the elements. We also introduce this connectivity element at each node of this composite SMIR finite element. Specifically on this figure C, it is presented node J as one connectivity node to couple between different physical fields. Now, here I introduce several assumptions for the formulation of general SMIR models for mechanics. CSF-EM consists from a supporting medium, or the basic medium here noted as B, in which are embedded other deformable domains. These domains are denoted as domain 1, 2, and etc. Relative velocities of domains are presented in each of the domain, and between supporting domain and compartments, we have interaction velocities with the compartments in direction of the boundary normal and tangent to the domain. Also, we have normal stresses at the interaction surfaces, and due to sliding between compartments and the supporting medium, we have tangential stresses. To be more precise, we calculate elementary surfaces between supporting medium and the domains 1, 2, or how many they are presented here, and between two compartments respectively. Also, we calculate the geometrical projections of these surfaces, and further, when formulating finite element model, we introduce connectivity elements at the boundaries, nodal parameters, and fibrous structure embedded within these continuum constituents. Now, Finite element representation of composite smear finite element for mechanics is given on this figure below. Here you can see that the element volume is composed of the supporting medium with this index B and different domains with volumes 1 to n. The nodal degrees of freedom include velocities in coordinate directions and tangential and normal components for the domain boundaries. Connectivity elements, they couple velocities at the boundaries of the different domains, and the volume of domains are specified by volumetric fraction, as in case of field problems, so that the volume fraction of the supporting medium is RV and every other domain is 1 minus RV. Nodal tangent and the normal forces due to connectivity elements in direction of global axis X is presented here as Ft or Fn. And finally, we present extension of CSF-EM to fiber-like continuum domains. There are various media with fibrous structure and extracellular space or cell interior with cytoskeleton, and from the practical implementation, it will be desirable to have a continuum representation of complex network of fibrous structure. Here on this figure below, on A figure is presented cytoskeleton within a cell. That is some MRI snapshot and equivalent sketch of fibrous structure in B part of this figure. To formulate this fibrous CSFM model, we have reference configuration and input data for fibrous structure such as number of fibers, volumetric fractions at nodal points, initial cosinus at nodal points, diameters of fibers at nodal points, and material data such as linear elastic material and Young's modulus for nonlinear curves. Accuracy of this smeared finite element methodology in mechanics is tested on several examples, from simple test example to detailed model with cells and surrounding tissue. First, we have tested this smeared model accuracy on simple test example of a square model with constraints and prescribed forces in x direction. We included slipping between compartments and supporting medium, and on the left, they are presented surrounding domain data with linear elastic model used as material model. We have two embedded compartments with different volumetric fractions, area fractions, and different Young models used in material. Number of time steps is 40 and duration is 0.5 second of each time step. So, field of displacements in x direction for supporting medium and compartment 1 of the model is given for two different time steps. Here are presented maximum strain levels, and as you can see, supporting domain has greater values of displacements due to applied force on its right part. Compartment 1 is not loaded, and such as that, he follows supporting media tension with appropriate displaced configuration. Now, also for compartment 2, we have field of displacements in x direction, where you can see that comparing to supporting medium and compartment 1, this compartment 2 has lowest displacement values. This is also compared on this diagram on the right, which shows input force function and compared values for displacements of supporting medium, compartment 1 and compartment 2. And here given maximum tension in x and y directions. As you can see, highest displacement value is for supporting medium because it is directly loaded, and difference between displacements for compartment 1 and compartment 2 lies in applying 10 times larger resistance coefficient between compartment 1 and supporting medium than between compartment 2 and this supporting medium. When accuracy is confirmed on this test example, we apply this methodology to compare results for detailed model of cells embedded in tissue space, also loaded with force on the right side. Domain data is given here on the left, where you can see that the number of cells is 45, material model for surrounding domain and cell is linear elastic, and equivalent smear domain has the same geometry, but significantly decreased number of finite element nodes, which is our goal, with supporting medium and one embedded compartment which represent one type of cells presented in this detailed model. Here we can see displacements for 3 different time steps for both detailed and smeared model compared. Material model and parameters are the same for all groups of elements, so Young models in surrounding domain is equal to Young models in cells and compartment. It can be seen that we have pretty good matching between displacement of a detail model and smear models for every presented time step. That was our goal, to show that this detail model, which declares significant effort for modeling, can be replaced with equivalent smear model with significantly decreased number of finite elements. Also, we here try to show results for detailed model with cell compared to smeared equivalent model. And here you can see displacement field for 3 different time steps. Material model is linear elastic for all domains, but parameters are not the same for all groups of elements. Young models in surrounding domain is 2 times larger than in cells and compartments. This was done in order to try different material parameters for different type of cells and to avoid unified material parameters. We here have a reasonably good matching between detailed model and smear models results for every presented time step. And this is something that should be investigated and improved in future. So to conclude this talk, we think that smear concept offers a broad theoretical basis for applications in problems of physical fields. Smear methodology extended to mechanical problems can serve as a starting approach with possible improvements also and corrections in further applications of this concept to various complex problems in biomedical and general engineering and science. Also, this further development of smear methodology with fibrous structure extension can lead to development of smear representation of detail and complex cytoskeletal network structures inside cell models. And to finish this talk, I just want to acknowledge support of Research and Development Center of Bioengineering in Kragujevac, Serbia, also Ministry of Education, Science and Technological Development of Serbia, Houston Methodist Research Institute, and University of Kragujevac and Faculty of Engineering. This work is also supported by the Silico FCM project that receives funding from the European Union's Horizon projects and innovation program. Also, this research was funded by Ministry of Education and Science of Serbia with these 2 grants presented. That's everything. Thank you for your attention, and I wish you a great health. Goodbye.